Hello everybody and welcome to Deep Learning with Pytorch Lesson 8. This is a very good lesson. We're going to start Chapter 5. And Chapter 5 is the mechanics of learning. So we're going to build a few models. They aren't going to be neural network models. They're just going to be basic models where we learn how to use the gradients, we're going to learn some important definitions from loss function. We'll get a little bit of an idea of how to optimize what's called the optimization function, although we won't be explicitly using one of the better optimization functions. We're going to be using a very basic one. So the chapter starts off and it kind of talks about Johannes Kepler. And what Kepler did was he basically looked at all the planets and how they moved for about 6 years and recorded it with just, on paper. And over time, after gathering all of that data, and I think he used his mentor's data as well. So seen with the naked eye, just examining the planets, and he developed some formulas, geometric equations on how the planets rotated around the sun. And later this data was used by Newton to come up with Newton's laws of gravitation. So in a way, this is an example of creating a model. If he had access to neural networks, he could have used neural networks to create the model, but he didn't. So he could only fit it into geometric equations. Essentially, he took a lot of data and fit it into a model and made Kepler's first and second laws. He wasn't able to apply the laws of gravitation to it because they hadn't been developed yet. Newton hadn't come along yet. So he just, to sum it up here, this is what it basically says. He got a lot of data. He tried to visualize it. So this is the same steps that we do when we're applying machine learning or neural networks to problems that we have today with data. Only we have more tools in our toolbox than he did. So that's why it's so impressive that he was able to do this. So he tried to visualize the data. He looked at it from a lot of different ways. Then he chose the simplest possible model to fit the data, which was an ellipse. So just a geometric equation. He split the data so that he could work on part of it. So he literally he took some of the data out of the set and left that data out, applied his models to another set of data, and then put the data that he left out, which you could technically call a validation set. He started with tentative eccentricity and size for the ellipse and iterated it until the model fit. So he tried certain sizes for the ellipse, certain shapes for the ellipse, and fit it so that it would eventually fit the planets. And he validated his model on independent observations and then looked back on disbelief. So he basically just created a model for which the planets rotate around the sun. So learning is just parameter estimation. Parameter estimation. That's all it is. Here is a good graphic of that. So we have some inputs. We feed it into our neural network or whatever our model is, and we change the weights so that we decrease the errors. So we have certain parameters. We're going to adjust those parameters, and we'll see the errors after it goes through. So it goes through, and we say, oh, that's a bad one, that's a bad one, that's a bad one. Okay, re-update it. So it goes back. You change the weights, you feed it forward again. Errors, change weights, feed forward again. So this is an iterative process until eventually we get the desired outputs, which are similar to the ground truth. And then when this whole process is done, we have another set of data down here that we feed through it and see if our model can be validated. So we don't just test it on our training set, we also have to test it on our validation set. So it's a whole process. So what they come up with here in this book is they say, hey, you got a new thermometer, right? You went to a store and you bought a fancy thermometer, but the numbers don't match up. So, okay, so TC are the temperature values in Celsius. So you have two thermometers. One's your old thermometer. It's your trusty Celsius thermometer. And then you have this unknown thermometer that you bought at the store. And it's given these values, which seems to be related to the old values. Like they seem to have the same shape. When this one goes up, that one goes up. So what you want to do is come up with a model that we could translate it back to this one, so that we can use this unknown thermometer and feed that data into our model and come up with the Celsius data. So all we're doing is creating a model for this data to predict this data here. Our unknown thermometer and our known Celsius thermometer. You could probably guess where this is going by looking at the temperatures, but we won't say anything like that yet. So here's our measurement. This is it on a plot. Here's our measurement of the data on the x-axis and the actual value. So it's not too complicated. We can see that it looks like a linear relationship. We could just apply a simple linear regression, but we're not going to do that. Actually, no, we are going to do that. We're going to apply linear regression to solve this. But let's go to the code and estimate the parameters here. So I've added some stuff to this code as we go through so that I can explain it as well as I possibly can. The first thing that we need to get a grasp on is, or we need to finish getting a grasp on, is what is called broadcasting. So let's go down to the broadcasting section right here. Broadcasting, which is popular in NumPy and adapted by Pytorch, relaxes this assumption for most binary operands. It uses the following rules to match tensor elements. For each index counted from the back, if one of the operands is size 1 in that dimension, Pytorch will use a single entry along this dimension with each of the entries in the other tensors along this dimension. So if we have a one-dimensional vector of size 10 and a one-dimensional vector of size 1, it will apply that one number, and we multiply those two. What broadcasting means is we will apply that single digit across the length of the 10-digit one-dimensional vector. And let's look at that in code form. So let me restart and clear output. We're going to import torch. We're going to make a torch ones, and when there's nothing in there, it's just going to be a single digit tensor with a 1 in it. This one's going to be a 3 by 1. Z is going to be a 1 by 3. And A is going to be a 2 by 1 by 1. Okay, so let's run this code. So here are the shapes of our tensors. Nothing, 3 by 1, 1 by 3, and 2 by 1 by 1. Okay, and they're all filled with 1s because it's torch.ones. So when we multiply x times y, our x is, let me add one down here. We're multiplying this tensor by this tensor. So all we're going to do is multiply that single 1 to each one of these ones. So our resulting one, print x by y, is essentially just y. So x times y, the torch size is going to be 3 by 1. What if we do y by z? Well, we have a 3 by 1 times a 1 by 3. So if we look at our y, we have that. If we look at our z, we have that. And we look at our y by z, we get that. So in the column that we have a 1 in, or in the dimension that we have a 1 in, we just broadcast that across the other dimensions. So what about A? Now we have a whole nother dimension, right? We got 2 by 1 by 1. So what do you think y by z is going to be? Sorry, what do you think y times z times a would be? Well, here's our a. Let's look at a. All right, that's our a. 2 by 1 by 1. Our y times z, we just did that, so we know that that's a 3 by 3. So we're essentially multiplying a 3 by 3 multiplied by a 2 by 1 by 1. So we should get 3 by 3 by 1. Let's see. Or 2 by 3 by 3. It's written right here. So let's look at the size of this. Y times z times a is that 2 by 3 by 3. And that's because the 2 is in the new dimension here. Okay, so that's called broadcasting. So this is the benefit of using Pytorch. It's able to do this. In NumPy, if these were NumPy arrays, you would get an error for multiplying these matrices. But because we're in Pytorch, that's the benefit of it. And that's what makes this coding language so robust. All right, so we're going to import NumPy as np and import torch, set our print options to 2 and our line width to 75. Let's run that line of code. Now we're going to input our tensors. This is our Celsius. This is our unknown. So if we look at our TU shape, we have 11. Our TC shape should be the same thing. So before we let's say we didn't run these. This is a list. So if I run it again, we'll get an error, right? Because these lines of code here are converting the list to a tensor. Torch.tensor converts this list to a tensor. We could also convert it to a NumPy array or whatever we want to, but we're going to convert it to a torch tensor. So I guess here we're just plotting the points, which we already saw in the book. So we know that there's basically a linear relationship here. So now we're going to use the definition line of code. And what this is doing, you use this for a function. I could write any function I want. Here are the inputs to my function, and here is what it outputs. So let's define this model. Okay. And now let's define a loss function. So we don't want to write every single thing we do mathematically, but this is very simple to see that that is the linear formula. That is y equals mx plus b. Okay, w is our slope, tu is our x, and b is the constant. So the way that we're setting this up is w is our weights, T sub u is our unknown temperatures, that's our input values, and B is the bias. All right, so if we wanted to calculate a loss function from that, what we would do is say TP equals, and so T sub P is predicted, right? That's what our model will essentially output, is a predicted value. We want to input our unknown temperature and have a predicted temperature, and we want the predicted temperature to be very close to our Celsius temperature. So we're taking the difference of those two. T sub P minus T sub C squared. Okay, so let's go ahead and run that. Now we are going to create a ones matrix for our W's and a zeros matrix for our B. And when we run this, we will see that let me add a line below this, and I'll say T underscore U, our unknown. So what model did here, when we plug in TP, we have a model which was explicitly defined right here. So we're taking our weights and multiplying it by our unknown temperatures and adding the bias. So we're taking our weights, which is W, which is a matrix of 1, and multiplying it by our unknown, TU, which is right here. So when you take this matrix and multiply it by 1 and add a 0, you get the same matrix. TU is the equivalent of TP thus far into the code, because all we are doing is multiplying by 1. That's all we've done so far. Multiply by 1, which is our weight, and add a 0. If we changed this to ones, we would be adding a 1. So then all of these numbers would go up by 1. So we run it again. Now we've added a 1 to it. We go back to 0. And we're back to normal. Okay, so far we haven't done anything. We've just created what our model is. Okay, so what do we need then? We need a way to change our W and our B to fit this data. We want to just turn the knob, and they have a little picture in the book, which is kind of neat, where he changes the W and the B, and he just kind of turns these knobs until he gets a good optimization. So that's what we want to do. We just want to maybe make our W a little bigger, maybe make our B a little smaller, but we don't know which way to turn the knobs or anything like that. We do have a loss function, but that doesn't tell us, which way to go. It just tells us how far off we are. So, and we'll see that in this line here. We're going to compute our loss function initially. This is how much our loss is before doing any type of optimization. Okay, so we got a very big loss. We got 1,763. That is our T predicted minus our T Celsius. This squared, right? We raise that to the power of 2, and then we take the average of each of those. Since this is 11 long and this one is 11 long, after we square it, we'll have 11 values. So we just take the average of those 11 values, and we end up with this value. So our loss is pretty high. We want our loss to be smaller than that. This is just the same broadcasting code from earlier. I'll just run that to show you again, but we'll just keep moving along. So now we're going to say, hey, let's change our W. Let's figure out a way to change our W a little bit, and we'll call that delta. We're going to change it by 0.1. All right, so the loss rate of change of W, let's define that, is going to be the loss of the model W plus delta minus the loss of the model W minus delta over 2 times delta. And I don't know if you're familiar with finite difference, but this is looking a lot like finite difference at this point. So we can run that code, and then let's see what the loss is initially. Okay, so we got a huge loss on W initially. Here we have the learning rate. So I commented this out because we got to really think about this stuff, because it'll make the other stuff more clear when we get there, when we start iterating over it. So let's set our learning rate e to the negative 2, which is just 0.01. All right, and now we're going to compute a new W. So our new W is going to change, and it's going to change based on our learning rate multiplied by the loss rate. So what did that end up being? Now our W is this huge negative number. Our W used to be 1, but because our loss was so high, it says, okay, that's going to be negative 44. The slope of your line is going to be negative 44, which right off the bat we can say that slope does not look like it should be negative 44, but let's keep going because we're going to learn something from this. Now, there are two parameters, and that's a key vocabulary word, parameters. W is a parameter, and B is a parameter. So let's calculate the loss of B, and we're going to do it the same way. We're going to calculate the loss of our model, and remember, loss is up here. There's loss. There's our model. Loss is rewritten here, redefined as just loss, but loss is listed right here. It's the squared difference, the average of that. And our model is just this linear y equals mxb equation. So you could write this down mathematically and do it on a piece of notebook paper to really get what's going on. But we're calculating the model with b plus delta, and then calculating the loss of that. Then we're subtracting b minus delta and calculating the loss of that. And then dividing by 2 times delta. And our delta was 0.01. Or sorry, it's just 0.1, so it's pretty high. Let's go ahead and do that for b. So b, it says, hey, that's way off, okay? Negative 4,600 is your new b. Or sorry, no, that's the loss for b. Now we're going to calculate our new b. And our b is going to be our original b, which was 0. 0 equals 0 minus the learning rate, e to the negative 2, multiplied by the loss rate, negative 4,600. What is b now? b is 46. So our new equation is t predicted equals negative 44 times t unknown plus 46. All right, well, let's see how good that does. So this is our new predicted matrix. So we inputted our, and let's just add a line right here. T. This was our input, our unknown temperatures, and this is what our model predicts now. So our model's obviously not very good. These values are not correct. What we want is, we want this to be our input, and we want this to be our output. Right now, this is our input, and this is our output. So we're way off. And if we calculate the loss, we can see that our loss went up significantly. Our loss was initially smaller. After one iteration, our loss has gone up. What can we do in here to change that? Well, maybe we could lower this learning rate to e to the negative 4. Let's try that. So let's restart this code. And let's try it out. Because our learning rate is how far we step in the correct direction. So now you can see that our W did not change so much. Last time our W was like this huge number. So by lowering the learning rate, we have improved our code. So this is our predicted. This is our input. This is our desired output. And this is the output that we're getting. So if we look at our loss, did we record our loss earlier? 1,700. Our loss went down to 323. So which part of the code would we rerun in order to do another iteration? We would have to start from right here. No, we'll have to start from right here. Okay, because this is our loss rate of change for W. So we rerun this. We're just rerunning all these lines of code. And now our model should improve once I run this line. And our model did. It got a little closer. And our loss function should go down. And it did. It went to 79. So we've done 2 iterations. And obviously you could loop this, but just to really show you, we'll do it one more time. Let's run it again. And our model is looking a little bit better. And our loss function continues to go down. So if we keep going, it should continue to go down. Now, why did lowering the learning rate increase our ability to get a more accurate function? There's a good sketch in this book on why that is. If I could figure out what page it's on. Page 118. So this is an example of a learning rate that's too high. What we're trying to do, and this is a calculus problem, we want to compute the minimum of this function, which is right here. We set our learning rate and we overshot the minimum. Okay, so now we're right here. Well, then we overshoot it again. All right, now we're right here at number 3. And then we're just going to overshoot it again. And we're going to wildly diverge because our learning rate was too large. Now, what about DEF? This is a much better way to do it. Our learning rate goes here. We get a little bit closer. Okay, and then it gets here. We're a little closer. And we're slowly working our way down to the minimum. And that's what we want. So there are ways to better do this rather than arbitrarily picking a learning rate. And one of those, or also the loss function that we calculated, we could determine the slope of that loss function using the derivative. So if we can determine the slope of our loss function using the derivative, that's called the gradient. The gradient is similar to the slope. So we calculate the slope of our loss function, and we'll learn how far to tune it in order to improve our model. So that's what we're going to define next, which is d loss fn. And what this equation is the derivative of our loss function. So we used to have T predicted minus T Celsius squared over the average. The derivative of that, the derivative of a square of something squared is just going to be 2 times that something. So that's what we have, 2 times that something over the derivative of the average, which is TP dot size 0, which is 11. So let's go ahead and do this. And boom. We got it. Okay? This is our derivative of the loss function, and this is the output of that. All right, now we're going to do the derivative of dw. Okay, so what was our w before? How do we update our w? We updated our w using this equation. No. Delta w. So we're taking the derivative of the model with respect to w. Okay? Our model was w times t underscore u plus b. That was our model. If we take the derivative with respect to w, we get tu. That's it. So that's why this equation just simply returns tu. All right, what if we take the derivative of this equation with respect to b. Let's run that. We'll skip this line. I'll delete it in a second. The derivative with b, this all doesn't have to do with b, so that gets deleted. So the derivative of 1 times b is 1. So the derivative of our model with respect to b is 1. So now we have two gradient functions. One is for delta w, one is for delta b, and we also have this one, which is the derivative of our loss function. Let's see what dp looks like. Okay, it's the equation returns a 1, so we plug it in and it returns a 1. This one returns a tu, so we plug it in and it returns our tu, our unknown temperature recordings. Now we're going to define the grad function. So our grad function's inputs are listed here: tu, tc, tp, w, and b. Those are the inputs for it. So we're going to take the derivative of the loss with respect to tp. Well, that's just going to be this. We already defined that. It's listed right here. All right. Our derivative of our loss with respect to dw. That's going to be the derivative of the loss with respect to tp multiplied by this equation here. And then derivative of the loss with respect to b is derivative of the loss with respect to tp multiplied by the derivative of the model with respect to db, which was listed here. Now we just stack that. So we've calculated the gradient of each of our variables within our model. Remember that our model was this guy here, weights multiplied by tu plus b. That was our model. So all we're doing is calculating the gradients of that model and the gradients of the loss function of that model. So feel free to write these down and compute them by hand if it gets a little confusing. Now let's calculate the grad function. So what does it return? It returns a torch stack of the loss with respect to w and the loss with respect to b. Our two parameters that we want to change. And it's the sum of those two parameter changes. Now, one is 315 and one is 8.53. Another thing we have to explain real quick is what is a stack, and what's the difference between torch stack and torch cat? Because we have used concatenate, we haven't used stack yet, and there's a great answer given right here. Stack concatenates a sequence of tensors along a new dimension. Concatenates the given sequence of sequence tensors in the given dimension. So if we concatenate A and B, dimensional 0 will be the shape of that. But if it's stacked, then it will do it along a new dimension. So that's what we did here. So we've calculated our grad function. Now we're going to do a quick training loop of that. Epic, new vocabulary word, is one complete cycle through our training data. So, in this case, our training data is 11 numbers. It's quite small. So, and technically our batch size is one number at a time. So, or actually I think our batch size is all 11 numbers. So we're just running the batch in one foul swoop. So W and B are our parameters. TP equals the model of TU W plus B. That was the linear equation. Our loss function is the same as the loss function was before. It is TP minus TC squared over the average of them. And then our grad function, which was listed right here. So we're calculating all of those things. And then we are going to update our parameters by subtracting the learning rate, which is whatever we assign it to, multiplied by the grad. And our grad here was 315, 8.53. So let's run that. Now this might get confusing, but this is the same thing. Okay, this is the same code. It just wasn't given in the book. And I will explain what these lines of code do in a minute. It's not complicated at all. So now we are going to use the training loop. And we have to define some things. What do we have to define? The number of epochs. We have to define a learning rate. And we have to define our parameters, initial parameters. It could be a random guess, or it could be 1.0 and 0 like we did before. Okay. So what happened here? It looks like the same thing that happened earlier, right? It exploded. Our loss function went from 1700 to this number, to this number, to this number, to infinity. Our solution exploded. Why? Because our learning rate was too large. Okay, that's one reason why. There are other ways to tune it to get your solution to converge. But the first way we will look at here is by making the learning rate smaller. So when we run it now, it does not blow up. Our loss function has gotten significantly smaller. So it looks like we're on the right track here with our loss function being smaller. Let me explain this line of code here now. We are telling it, here we're telling it to print the epoch and print the loss for each of the epochs. So this line of code is what creates this. Okay? It creates this line. Epoch, what epoch are we on, and what's our loss? This one is just a little bit more stuff in it. It says only print the epoch if it's in 1, 2, 3, 10, 11, 99, 100, 4,000, or 5,000. Okay? So we can see that 1, 2, 3, 10, 11. And then on this one it says print a ... on these given epochs. So that's why we have the ... And it also says, hey, we want to look at the params and the grad as well. So this is our grad each time. You can see how large the grad is getting. So when you hear people say, like, I'm praying for small gradients, that just means they want their gradients to not explode and ruin their training. So what's another way? I told you that we could adjust the learning rate in order to get this solution to converge. What's another parameter that we can tune? And that's not the correct word to use. We're not tuning a parameter here. Our parameters are B and W. These are hyperparameters. We're tuning the learning rate. That's a hyperparameter tuning. If we're tuning the number of epochs, that's a hyperparameter. Or if we're tuning our gradient function, that is called hyperparameter tuning. Our parameters are the things that have to do with our function, which is W and B, our weights and our biases. So let's run this line of code here. What is this doing? We are scaling our initial TU we just scaled our initial tensor. Our unknown temperature predictor was about 1 power higher. So we're just scaling it by 0.1. So if we look at T, I don't remember what it was called, TC, these numbers are a little bit closer to these numbers now. So we just scaled it. We don't all, that's, like I said, there's more than one way to do this, but this is just showing you that it works. Now our learning rate is set back to 1e to the negative 2. And our solution doesn't explode. So that's very fascinating, right? I mean, it exploded before when we used this learning rate, but because we scaled our initial input tensor, it no longer explodes. And you can just see that from the loss. The loss is going down after each iteration. That's what we want. We end with the loss of 22. This one ended with the loss of 29. So this is actually approaching the solution faster. All right, now let's really train this thing, okay? Let's up the number of epochs. We've been training on 100 epochs. Let's go ahead and do 5,000 epochs. Let's set our learning rate to e to the negative 2. We're going to scale it, and we're going to do it. Let's go. All right, we get all the way down to a loss of 2.92, and it looks like it's beginning to converge there. We'll talk about how to compute the convergence in the next video, or at least some part of that. We'll also talk about better ways to optimize our functions, but we can see that we end on 2.92768, and then 1,000 epochs later, we only get down this 8 to a 4. A 4.8, so it didn't go down very much in the course of 1,000 epochs. Initially, it decreases substantially. So let's look at our plot here. Looks like a pretty good prediction, right? This is our predictive function here, y equals mx plus b, and it looks like it is predicting these points pretty closely. And of course, here's the initial plot. These were the final values here. So this is our W and this is our B. Our W needs to be scaled back. And that's it. So I plugged in, I scaled the W back, multiplied it by our TU, and then subtracted our bias. If we look at our T underscore, sorry, I meant to do that here, T underscore C, they're pretty close, right? They're not dead on, but our predictions from our measurements are pretty close. And what was the main purpose of this whole thing? We just did an entire thing on converting Celsius to Fahrenheit, right? Our unknown temperature was, spoiler alert, it was actually a Fahrenheit thermometer. So the equation for Celsius is actually 9/5 Celsius. Oh, well, I guess we want to go Fahrenheit to Celsius. Which is going to be 5/9 multiplied by x plus 5/9 multiplied by 32. So let's add something here. What is 5 divided by 9? 0.55. When we scale that, we got a 0.53. So we're pretty close to that. And in the book, they actually give it to you as well, the actual values. This is an estimation. 17.7. We're pretty close to that as well. We're at 17.3. In the book, they do tell you the exact values for that here. The exact values would be, they wrote 5.5. That's actually an error. It should be 0.5556. So our numbers were pretty close to that. Just off these sloppy measurements. That's the numbers that we computed. So that's all we did. Thank you for watching, and I'll see you in the next video.